Hi, I'm Ritwik. This video is a part of the pattern recognition course at University of Florida. Here I'm going to present a demo of my project based on sentimental analysis. Sentimental analysis is the computational study of people's opinions, attitudes, emotions towards an entity. The entity can represent individuals, events, or topics. These topics are most likely to be covered by reviews, movie reviews in our case. Sentimental analysis is an extremely useful tool with far-reaching applications. Shifts in sentiment on social media have been shown to correlate with shifts in stock market. The Obama administration used sentiment analysis to gauge public opinion behind certain topics. Big brands are known to consistently monitor user sentiments towards the products and keep introducing changes according to those sentiments. The sentiment analysis has two basic approaches. One is the machine learning approach, the other is the lexicon-based approach. We're not going to lexicon-based approach. The machine learning approach broadly classifies into supervised learnings and unsupervised learning. Supervised learning is the task of predicting from labeled training data. In supervised learning, each example is a pair consisting of an input object and a desired output value. The supervised learning algorithm analyzes the training data and produces an inferred function, which can be used for mapping new examples. The unsupervised learning is a type of machine learning algorithm used to draw inferences from datasets consisting of input data without label responses. In our application, we have implemented the decision tree classifiers using random forest, linear classifiers in the form of support vector machines, and probabilistic classifiers using a naive Bayes with different methods of feature selection and extraction. Now coming on to the problem. Now one can clearly see that categorizing the sentence as negative, positive, or neutral can be difficult. The phrases pleasing to the eye can be considered positive, and storyline was boring as negative. But the degree of positivity and negativity of the sentence is somewhat ambiguous. Apart from that, the grammatical structure of the text, abbreviation, etc. all have an impact in classifying the polarity of the text. My approach to the problem involves a comparison of different techniques for building the sentiment model. The techniques include various classification models as explained earlier, and various feature extraction and selection algorithms. It starts off by processing and cleaning the data. In the text pre-processing stage, we start off by the cleaning data, which includes tokenization, that is converting sentences into words, removing punctuations and symbols, followed by filtering of stop words. The stop words are not so useful words like as, from, on, the, to, etc. Now to obtain the feature vector for each review, we will compare the performance of two approaches, word-to-vec and TF-IDF. TF-IDF is term frequency inverse document frequency. This is using n-grams for feature selection. In case of word-to-vec, after learning the vector representation of words, we average all the vectors of the words in each review. For this project, we have used the Jensen library to generate word-to-vec representations. A 50,000 strong unlabeled review data was used to train the word-to-vec model. For the other approach, TF-IDF is used in conjunction with n-grams. We start by building a document term matrix for the given data, which indicates the sentences as rows and the corpora of words in the entire text as their columns. The values in the matrix are the frequencies of the words appearing in a sentence. The TF-IDF vectorizer method from scikit-learn library does the computation for us. Well, a point to note here is that since we're using n-grams of TF-IDF, we abstain from removing the stop words, as this would help the n-gram better understand the context of the text. Consider the case where there is a phrase like not good. This is obviously a negative connotation, but taking each word separately like good might wrongly assume it to be positive. Rather, bigram would probably learn that it is a negative sentiment taking the two words together. Probabilistic classifiers use mixture models for classification. We are using naive Bayes for this project, and the naive Bayes classification model computes a posterior probability of a class based on distribution of the words in the document. It uses Bayes' theorem to predict the probability that a given feature set belongs to a particular label. From the project, we have come to know that the naive Bayes algorithm performs better with TF-IDF with bigrams, and the word-to-vec method gives poor results. As shown in the graph here, the word-to-vec results for Gaussian naive Bayes display an accuracy of 71.94, and for multinomial about 75.86, whereas for TF-IDF using n-grams with 1:3 ratio. The Gaussian distribution shows 83.68 as accuracy, and the multinomial naive Bayes shows 87.23 accuracy. The next is the linear SVM. The main principle of support vector machines is to determine linear separators in the search space which can best separate the different classes. We come to know that the best performance that linear SVM gives is with TF-IDF using n-grams, and this is supposedly the best performance we got among all the algorithms we used, and it gives an accuracy of 89.22%. And similarly as the others, word to wake gives considerable results, but the average of word to wake does not make sense as it also ignores the order of words. Coming on to random forest. The random forest implements decision tree algorithm to learn a number of decision trees to make a classification decision. At every step of the learning process, an attribute is selected to split two or more different paths, and this process is iteratively repeated until the attributes are exhausted or we have reached a pure classification split. Random forest performs better than naive Bayes when using word to wake with 77.91 accuracy, but worse than SVM. It gives an OOB score of 0.082752 for TF-IDF, but random forest does not suit well in text data since it makes a split based on randomly selected features. Now coming on to the validation part, we have used tenfold cross-validation for the evaluation. The dataset is divided into 10 subsets, and each time one of the 10 subsets is used as the test set, and the other 9 subsets are put together to form a training set. Then the average error across all 10 trials is computed. The advantage of this method is that it matters less how the data gets divided. Every data point gets to be in a test set exactly once and gets to be in a training set 9 times. The variance of the resulting estimate is reduced as the number of subsets is increased. Although the disadvantage of this method is that the training algorithm has to be rerun from scratch 10 times, which means it takes 10 times as much computation to make an evaluation. The other parameters for evaluation of our algorithms are precision, recall, and F1 score. These are standardized evaluation metrics which define the number of true positives over the number of true positive plus the number of false positives. Precision, recall, and F1 score are used to calculate the efficiency and the performance of these algorithms. The result of our project is that the SVM, the linear SVM, performs much better than TF than naive Bayes and random forest algorithms with using TF-IDF and bigram unigram vectorizing. Linear SVM yields an accuracy of 89.22% and gives the worst accuracy with Gaussian naive Bayes using word to wake with 71.94%. As mentioned above, the word to wake does not make sense as it also ignores the order of the words. Now coming on to the demo.